Hi Jeremy, this is Cheng Zhengjiang. In this video, I'm going to demonstrate my work on project microgrid design with multiple objective optimization. The location I selected for my project is Rose, a small town with around 2,000 people living there and 1 km square large area. I'm going to design a 15-bus microgrid with battery, fuel cell, PV panel, and wind turbine. After analyzing demand distribution, the PV panels are going to place at bus 6 and bus 11, while the wind turbine are going to place at bus 9 and bus 14. The weather data are found on BOM Australia. This is installation and wind speed curve for 1 year. The electricity price data are found on AEMO. The feed-in tariff is 12.5 cents per kilowatt hour. Then is the devices selection. First is PV panel with important specification. Then converter for the PV panel. Then the wind turbine. Battery unit. Last one is fuel cell. In this project, I assume fuel source is natural gas. In terms of money, I assume the owner applied a 10-year loan with 6% interest. So with the individual prices, each component's daily cost can be determined. The output power of PV panels can be calculated by several formulas in which the temperature is involved. I fit a function of temperature for 1 year by using a daily temperature data and then obtain the PV output power for 1 year. The same method is applied for wind energy, and the wind output power is easy to get as well. The first stage optimization is for components allocations. There are two objectives, one is economy and another one is low carbon emission. I would like to show the equality constraint first. First one is power balance, and then DC power flow. Then is the battery energy consistency, but this one will not be used in matrix. Then the inequality constraint. First one is battery energy limit. The battery charge and discharge at time t plus previous energy stored in the battery cannot be lower than the minimum state of charge or higher than maximum state of charge. Then is the battery charge limit, battery discharge limit. Then is a grid transaction limit, but actually for this project, this boundary is really hard to reach. Fuel cell power limit. Moreover, there's an upper and lower bound for variables. Some variables should be integer. This is also need to be considered. Once the model is built, code cannot be a question, at least for now. Here's the optimization result for 1 year, but there's a problem. The quantity of PV panels, wind turbine changes significantly day by day, but I still want to pick one day to show the result. Here's a battery charge and discharge diagram. In my opinion, I think the problem is when weather is good, the system tends to use as much renewable energy as possible, so it wants more wind turbine and PV panels. Once the weather is bad, the system tends to use power from grid or fuel cells to reduce the daily cost. So the key question becomes, which electricity price is cheaper? I try to fix that. The first attempt is make the electricity price proportional to the grid power amount, which means the system become non-linear. And then I use GA or FMINCOM to solve that, but it turns out to be very time consuming. Then I created a carbon emission function and tried to use it as a constraint. Then I found it can satisfy the economy objective, because in these two functions, I want them to compromise each other. Later, I put a carbon tariff to make them into the same unit. I realized it's still price problem. Which kind of electricity is cheaper? Then I tried another way, which is I'm working on right now, is I'm trying to use different weight from 0 to 1 and set a acceptable range for carbon emission and cost. And then to find out which weight can make the result both within 2 range for the most days. I think it might work, but I'm still working on that. Maybe I don't need to make it complex like that, but the carbon emission should be considered at first stage. Once the PV panel and turbine quantity is settled, is determined, and always trying to produce as much renewable energy as possible, because if you don't use the renewable energy, you're losing money. Then after finishing this, I'm going to do secondary optimization, which involves demand response to reduce the peak time load, and PV and EV system, which means we don't need to sell electricity at low price when renewable energy exceeds our demand. Also, this strategy helps to reduce the power fluctuation to make this system steady. Hope I can finish all of this before next week. And that's all for my video content. Thank you so much for your time, Jeremy.